Now we will discuss the forced oscillator. Okay? And first, I would like to discuss the ideal forced oscillator. Ideal forced oscillator. And so we have an external force acting on the system. So this is, let's say, our ideal oscillator that we discussed before. Now we are applying a force on it, a variable force. And I will take one particular force, and we will discuss that. So the equation of motion, mx double dot, this is the acceleration, that's equal to minus kx, that's the restoring force, plus f of t, this applied force, and m x dot plus, again, m k over m x, that's equal to f of t, and k over m is omega, let's call omega 0 square. I will consider one particular type of force, and so if there was no force, this would be, we know the solution. We discussed this in the ideal case. If f equals 0, solution would be x equals a cosine omega 0 t plus b sine omega 0 t. Just ideal with f equals 0. But what if we have this f and I am considering f of t, a force that is driving this ideal oscillator at the resonant frequency. So f of t is equal to f0 cosine omega 0 t. Notice that I am just taking the omega of the force, the oscillation frequency of this ideal oscillator. We have to be careful in solving this problem because the point is this. This is why I'm starting with that. If you add to it any solution which involves sine omega 0 t and cosine omega 0 t, it will not work because those functions are here, and it basically redefines these unknown constants to be found from the initial conditions. Therefore, that would not work. So we have to try something else. So again, let me write this this thing in this form: x double dot plus omega 0 square x is equal to f0 m cosine omega 0 t. And let's again switch to the complex notation, which makes life much easier. X is equal to real x hat, and x hat will be, now this will be complex and oscillating with e to the I omega 0 t. That's the only oscillation frequency we have in the problem. But when we take the real part, some constant times e to the I omega 0 t, that I just mentioned, it would not solve our problem because cosine omega 0 t or sine omega 0 t is already here. Therefore, we try the next best thing. We multiply it by a complex f of t and try to find the simplest function f that gives us the solution. So I'm erasing these parts. So we will have x double dot plus omega 0 square x, that's equal to f0 over m e to the I omega 0 t, and the force is the real part. Real force is the real part of that. And x is this. So let's write x dot is equal to f dot e to the I omega 0 t plus f times I omega 0 to the I omega 0 t, or x double dot is f double dot plus I omega 0 f dot times this plus this thing times the derivative of that, f dot plus I omega 0 f times the derivative here, omega 0, everybody multiplied by e to the I omega 0 t. And let's now collect the terms. I have f double dot plus I omega 0 f, I omega 0 f, I omega 0 f dot, I omega 0 f dot, 2I omega 0 f dot so this is gone, these two are gone, plus or minus I omega 0 minus omega 0 square f times e to the I omega 0 t. This is the double dot part. I will add to it omega 0 square times x, which is f times. So omega 0 square x is equal to omega 0 square f e to the I omega 0 t, and I add them up. So they cancel. Let's write here what remains. F double dot plus 2I omega 0 f dot. Omega 0 squares cancelled. That's equal to, we put the force f0 over m, and e to the I omega 0 t's are the same factor. So it is f0 over m. We have to solve it for f. But remember, we asked for the simplest solution. So let us, to make it simplest, let us assume f double dot to be equal to 0. So if that's 0, we should attempt the solution of this equation. So df dt is equal to minus 1 over 2m omega 0 I, because 1 over I is minus I. Multiply I, divide by I square is minus 1. I have a minus I, 2m 0. 2m omega 0 times f0. So f df is minus I f0 to m omega 0 dt, and the integral of it is indefinite integral. F is equal to minus I f0 to m omega 0 t plus constant. Now, notice that this f is to be multiplied by e to the I omega 0 t. So the first term, t times e to the I omega 0 t, gives me a different term than simple sine omega 0 t or cosine omega 0 t. But the second term is constant times e to the I omega 0 t. And what is e to the I omega 0 t? It's a linear combination of cosine and sine omega 0 t. And again, you can dump it into the initial conditions, a cosine omega 0 t plus b sine omega 0 t. So this we will ignore because this will go to the initial conditions. So we have found x. X is equal to this thing, f0 over 2m omega 0 minus I times cosine omega 0 t plus I sine omega 0 t, and x is the real x. So the real x is minus I times cosine, that's imaginary, minus I times plus I is plus 1, so that term is the real part. That's f0 over 2m omega 0. There's a t here. That's why we did all this. T times sine omega 0 t. So we can write the full solution to this. I can erase this thing now. So the full solution is x of t is equal to a cosine omega 0 t plus b sine omega 0 t plus f0 over 2m omega 0 times t times sine omega 0 t. Okay, this is the solution. Let's talk a little bit about the physics of this thing. I have an ideal oscillator. It has a frequency omega 0. I am applying a force, a sinusoidal force that varies with the same frequency. Okay, with the same frequency. And if so, then the solution is this. Now notice something remarkable here. Sine and cosine are at most plus 1 and minus 1. But this t is increasing. So that oscillator is oscillating with bigger and bigger amplitudes. And finally, of course, that's the breakdown or the collapse of the system. System will collapse. Okay, this will drive the system finally to collapse. And indeed, if driving a system in resonance in this fashion persists, the system finally gets crushed. And an example of this, a historical example, although not exactly the same problem, but that can show how a system breaks down under resonant driving force, is the Tacoma bridge problem. Tacoma bridge collapse. That you can Google or YouTube and just, it's a famous case. It shows how this unfortunate case, the collapse of that bridge. Okay, so what we have done is we studied what happens if we drive ideal oscillator with a force of the same frequency. Now I give a homework problem or an exercise. Drive not by f0 cosine omega 0 t, but drive by cosine omega t, omega not equal to omega 0. In that case, such a function, since it's not cosine omega 0 or sine omega 0 t, it will not be t times that, but it will be simply a magnitude times of this type of function.